Now this sum of the forces kind of leads us to an interesting case, and that's going to be a case where an object is in equilibrium. If you consider, this fellow right there holding a bag of flour, so I'm going to kind of draw the bag of flour. Now what's pulling it downwards is going to be its weight. So there's going to be one force in that direction, which is simply going to be its weight, and it's being pulled upwards by this spring right here. So it has a support force just like that. And it turns out that if these two guys balance each other out perfectly, then we would say that the sum of the forces is equal to 0. So the tensional force is going to act upwards. It's going to have gravity pulling it downwards. They're the same number, they're equal in magnitude, but opposite in direction. So when they add together, then the net force on this guy is going to be equal to 0. So net force is equal to 0. So this bag of flour is going to remain at rest. And in a nutshell, that's kind of what the equilibrium rule says. If the sum of all the forces acting on an object are equal to 0, then it's not going to accelerate. And again, not accelerating means no change in velocity. Let's just kind of consider for a second two painters right there, and the painters have a little bit of weight. Suppose this guy has a weight of 100 newtons, and this guy right here has a weight of 50 newtons, and they're standing on this board, and the board also has a weight, and I'll just say that's going to be 50 newtons. Then as long as these guys are at rest, and we certainly hope that they are, then all of these numbers in green, 100 plus 50 plus a 50, so the sum of the forces in the downwards direction is going to be equal to 200 newtons, and that's kind of the sum of the forces. Now that little squiggly right there means it's a shorthand for sum of. Now as long as these guys aren't accelerating, then this force plus this force must also equal to 200 newtons. And if these guys were, if this guy was right over here and everything was nice and uniform, then we could probably say with certainty that there's going to be 100 newtons right there and 100 newtons right there. But as this guy starts to walk over to this side right over here, then more and more weight is going to be supported by this guy and less by that guy. So maybe it's no longer going to be 100 newtons and 100 newtons. Maybe it's going to be 150 newtons and 50 newtons. All that really matters is in the upwards direction that the sum of the forces is also going to be equal to 200 newtons, so that way it balances this guy out. So take a second and just kind of do a check on yourself. This equilibrium rule, the sum of the forces is equal to 0, is going to cause no acceleration. That is definitely need to apply to vector quantities. Remember, vector quantities have direction associated with them. Scalar quantities do not, and if we don't have any direction, then things can't cancel each other out. Now this idea of the equilibrium rule, it's going to have some practical applications. For example, if you take a book and you set it on the table, then you know that it's not going to be accelerating, it's just going to be sitting there. And so you ask yourself, what are the forces acting on this guy? Well, one of the forces is going to be due to the book's weight, which is actually going to be its mass multiplied by gravity. So we're just going to have its weight right down here. What's pushing it upwards? Well, the table is pushing it upwards, and the book's going to kind of compress the table a little bit, and the compressed atoms in the table are going to push upwards. So there's going to be some support force that's equal to the weight. So it's going to be opposite direction, equal number. So if the book has a weight of 100 newtons, then the support force of the table must also be 100 newtons in the opposite direction, and they're going to cancel each other out. We have a special name for this force. It's called the support force, or the normal force, which is just going to be what keeps objects from falling through tables, falling through floors in buildings, or whatnot. Now what this actually kind of looks like is a little bit like a spring. If you have a book on the table, it's going to, again, compress the table just a teeny tiny little bit, and it's going to provide that support force. This is kind of analogous to if you have a big coil spring and you push down on it, then you know that it's going to push back up on you. Essentially what's going on a molecular level at the table is it acts like a whole bunch of little tiny springs right here, and just like this spring right there, you compress them and they're going to push upwards. So let's just get a little bit of practice with this. Suppose, for example, you were to stand on two bathroom scales, 1 foot on each scale, and you distribute your weight evenly between the two of them. Then let's just kind of draw this guy right here. Suppose that you have the weight of 100 newtons, and you put it down there just like this. And you would expect each of those scales to push upwards with half of your weight. So you'd be pushed upwards by scale number 1, and scale number 1 may push up by 50 newtons, and scale number 2 would also push up with 50 newtons, and they would balance each other out, and you would not fall through the floor. Now, up until this point, we've talked about things being in equilibrium. Again, equilibrium means that the sum of the forces is going to be equal to 0, which also means that the acceleration is also equal to 0. And we've said, okay, things that are just kind of sitting there, obviously they are not accelerating. And we can have this idea of static equilibrium, in which case there's going to be no movement, and that's just going to be books on tables or whatnot. So we could have, example, a hockey puck sitting at rest on some slippery ice, keyword is being at rest, but we can also have something called dynamic equilibrium, where an object can be moving, but it can also be in equilibrium. Now, as long as it is not accelerating, and that's kind of the key word right here, so no acceleration. Now, and this is called dynamic equilibrium, and that's just when things are in equilibrium, but they're moving. So we could have a hockey puck that is on some slippery ice, so that's going to be my slippery ice, and we can have my hockey puck just like this, and as long as this guy is moving at a constant speed, then constant speed means no acceleration, then it can also be in equilibrium. Kind of the test that I want you to ask yourself is whether something is in equilibrium or not is going to be, does it undergo a change in motion, or is the velocity changing? Obviously, a crate at rest is in static equilibrium, there's no change in motion. If we had the same crate and it was pushed at a steady speed, keyword here being steady speed, it's not accelerating, velocity is not changing, then it is going to be in equilibrium, is going to be in dynamic equilibrium, so there's no change in the motion. So if we push on it with some force, then there's got to be some other force pushing back on it, for example, friction, and it's going to be equal in number, opposite in direction, so the crate's going to move at a constant speed. So just kind of run that test for yourself. A bowling ball is going to be in equilibrium when it is at rest, moving in a straight line path, so it's going to be both of these. And just kind of another test, suppose you push a crate at a steady speed, keywords being steady speed, and you know that there's 75 newtons worth of friction. How much force must you apply? It must be equal to 75 newtons and in the opposite direction.